Hi and welcome to John's Maths Book. In this video, we'll be exploring another key concept in mathematics. If you find this tutorial helpful, then please show your support by subscribing, liking, and leaving a comment. Your positive engagement helps me create more content and allows me to bring you more valuable maths lessons. Without further ado, let's go over to the whiteboard. In this exercise, we have two intersecting circles labelled here as circle 1 and 2. The region of intersection is shown in red. We are tasked with finding the area of the red region of intersection using double integrals and polar coordinates. The equation of each circle is shown in Cartesian coordinates. Circle 1 has a radius of 2 and is centred at the origin. Circle 2 has a radius of 2 and is centred at x equals 0 and y equals 2 and cuts the y-axis at y equals 4. The first step in finding the area is to convert the equations of each circle from Cartesian coordinates to polar coordinates. To do this, we'll substitute rcosθ for x and rsinθ for y. For circle 1, we have the equation x squared plus y squared equals 4. Making the substitution for x and y, we have r squared into the bracket of cos squared theta plus sin squared theta equals 4. Using the trig identity where cos squared theta plus sin squared theta is equal to 1, we have r squared is equal to 4. And taking the positive square root of each side, we have r equals 2. For circle 2, we have an equation of x squared plus y squared is equal to 4y. If we make the substitution for x and y, we have r squared into the bracket of cos squared theta plus sin squared theta is equal to 4r sin theta. Using the trig identity where cos squared theta plus sin squared theta is equal to 1, we get r squared is equal to 4r sin theta. Dividing both sides of this equation by r, we're left with r equals 4 sin theta. Now that we've found the radial distance r of each of the circles, let's look at the behaviour of r as we use it to compute the region shown in red. As r rotates in a counterclockwise direction from theta equals 0 to theta equals pi, theta being the angle it makes with the x-axis, the radial distance from the origin is first determined by circle 2. When circle 2 intersects with circle 1 for the first time at some angle of theta, the radial distance from the origin is then determined by circle 1 until it once again intersects with circle 2 at some angle of theta. At this point, and until theta reaches pi, circle 2 is used to determine the radial distance r. At theta equals pi, the area is complete. As this is a symmetrical shape, we could just consider the area from theta equals 0 to theta equals pi by 2 and double it to get the total area. However, for this exercise, I'm going to consider the area as 3 sectors from theta equals 0 to theta equals pi and sum the 3 to get the total area. Have a go at the first option where theta rotates from 0 to pi by 2 and let me know in the comment section what answer you get. To find the angles of theta where the two circles intersect, we can set the polar equation of circle 1 to be equal to the polar equation of circle 2. So the equation for circle 1 is r equals 2 and the equation for circle 2 is r equals 4 sin theta. Equating these gives 4 sin theta is equal to 2 and therefore sin theta is equal to a half. As we rotate counterclockwise from theta equals 0 to theta equals pi, the first time sin theta equals a half is where theta equals pi by 6 radians. And the second time sin theta equals a half is at 5 pi by 6 radians. So we now have the two angles at which circle 1 and circle 2 intersect. We are now in a position to start defining the limits of integration as r rotates about theta, which will be our outer integrals. The area of our region of intersection r can be defined as a double integral over the region r, where we sum infinitesimally small pieces of area shown as dA. In this exercise, the region, as we saw, is split into three distinct sectors, each represented by a double integral. In the first sector, theta started at 0 and continued to where theta is equal to pi by 6 radians. These form the limits of integration of the outer integral of our first double integral. We then saw that the second sector began where theta equals pi by 6 radians and continued to where theta is equal to 5 pi by 6 radians. These forming the limits of integration of the outer integral of our second double integral. Finally, we saw that the third sector began where theta equals 5 pi by 6 radians and continued to where theta equals pi radians. These forming the limits of integration of the outer integral of our third double integral. Now let's look at what happens when we sum infinitesimally small pieces of area along the radial distance or in the r direction. This will help us define the inner integrals. When we integrate in the r direction, this will represent the inner of the two integrals. This diagram represents a sector of the region capital R. The angle it makes is infinitesimally small and is denoted by d theta. Within the sector, we have infinitesimally small pieces of area denoted by dA. The size of each area is the length multiplied by the width. So in this case, dr is the length and r d theta the width. So dA is equal to r dr d theta. To find the total area of the sector, we integrate or sum in the r direction. In the first sector of area, when we sum or integrate along the radial distance r, we begin at the origin and travel along the perimeter of circle 2 until circle 2 intersects with circle 1. So we begin at r equals 0 and end at r equals 4 sine theta. In the second sector of area, when we sum or integrate along the radial distance r, we begin at the origin and travel along the perimeter of circle 1 until circle 1 intersects with circle 2 again. So we begin at r equals 0 and end at r equals 2. Finally, in the third sector of area, when we sum or integrate along the radial distance r, we begin at the origin and travel along the perimeter of circle 2. So we begin at r equals 0 and end at r equals 4 sine theta. Now we can add in the limits of integration of our three sectors when we integrate or sum along the radial distance r. In the first sector, we saw that our lower limit of integration was at r equals 0 and our upper limit was at r equals 4 sine theta. In the second sector, we saw that our lower limit was at r equals 0 and our upper limit was at r equals 2. And finally, in the third sector, we saw that our lower limit was at r equals 0 and our upper limit was at r equals 4 sine theta. And we saw that in each of the integrals, we are summing infinitesimally small pieces of area, dA, which translates to r dr d theta. We can now start evaluating the inner integrals. The first of these is the integral from r equals 0 to r equals 4 sine theta, r dr. Using the power rule, the antiderivative of this is r squared divided by 2, which we need to evaluate between 0 and 4 sine theta. Plugging in the values for r, we get 8 sine squared theta. In the second of our inner integrals, we want to integrate between r equals 0 and r equals 2, r dr. Using the power rule, the antiderivative is r squared divided by 2, and we need to evaluate this for values of r between 0 and 2. If we plug in these values for r, we get a value of 2. And in the third of the inner integrals, we want to integrate between r equals 0 and r equals 4 sine theta, r dr. Using the power rule, we find that the antiderivative of this is r squared divided by 2, and we need to evaluate this for values of r between 0 and 4 sine theta. If we plug in these values for r, we get an answer of 8 sine squared theta. And now moving on to the outer integrals, the first of these is the integral between theta equals 0 and theta equals pi by 6, of 8 sine squared theta d theta. The antiderivative of this is 8 into the bracket of theta divided by 2 minus sine 2 theta divided by 4, which we need to evaluate between 0 and pi by 6. If you're wondering how I evaluated the integral of sine squared theta, please watch this video I made for a step-by-step solution. And plugging in the values for theta, we get 2 pi by 3 minus the square root of 3. For the second of the outer integrals, we want to integrate between theta equals pi by 6 and theta equals 5 pi by 6 to d theta. And using the power rule, the antiderivative is 2 theta, which we need to evaluate between pi by 6 and 5 pi by 6. And plugging in these values of theta, we get 4 pi by 3. And for the last outer integral, we want to integrate between theta equals 5 pi by 6 and theta equals pi, 8 sine squared theta d theta. And the antiderivative of this is 8 into the bracket of theta divided by 2 minus sine 2 theta divided by 4, which we need to evaluate between 5 pi by 6 and pi. If you're wondering how I evaluated the integral of sine squared theta, please watch this video I made for a step-by-step solution. And plugging in these values for theta gives 2 pi by 3 minus the square root of 3. To find our total area, the only remaining thing to do is to sum the values obtained from the double integrals. So we have 2 pi by 3 minus the square root of 3 plus 4 pi by 3 plus 2 pi by 3 minus the square root of 3, which evaluates to 8 pi by 3 minus 2 multiplied by the square root of 3, which is our final answer.